Hi students, welcome to physics class. Today we will discuss about how a solenoid behaves as a bar magnet. We know that a solenoid is a long cylindrical coil of n number of turns. It is represented as this one. This is a solenoid in cylindrical shape having n number of turns. In order to understand the solenoid, first understand what is a current carrying circular coil. A circular coil which is carrying current I can able to produce a magnetic field. This is the result of Oersted experiment. Oersted said that a straight conductor carrying current or a circular coil carrying current I can produce magnetic field. We know that for a circular current carrying coil, on the axial line the magnetic field is given by B is equal to mu naught capital N into I into R square divided by 2 into capital R square plus X square whole to the power of 3 by 2. Here N is number of turns and I is the current in the coil. Capital R is its radius and X is the distance of the point P from the center on axial line. And we know that as x tends to 0, in this expression as x tends to 0, then in the denominator it remains only 2 into r square whole to the power of 3 by 2. By cancelling 2 we get 2 into r cube. That is, in the denominator we get 2 into r cube. In the numerator we have r square. By cancelling we get B at center. As x tends to 0, the magnetic field at center is given by mu naught N into I by 2R. If the current is in anti-clockwise direction, then the side which is facing towards us is a north pole and the face which is facing opposite to this side is a south pole. That is, when the current is passing through a coil in a clockwise direction, the side which behaves as south pole. That is, for a same coil, if current is in anti-clockwise direction, then this side facing towards us is a north pole and other side of this coil we can say that the current is passing in a clockwise direction and that side is a south pole. For same coil, south and north poles. So the coil behaves as a bar magnet which possess north and south poles. These two poles are always together. There is no monopole exist in nature. Now our aim is to prove that a solenoid which is carrying current I can behave as a bar magnet. Here the solenoid has a length 2L. The length of the solenoid is 2L. Small n is the number of turns per unit length. That is for total length. Total length is 2L. That is from plus L to minus L. So for total length of the solenoid, the number of turns is equal to small n into 2L. So from this expression, B axial of solenoid is equal to mu naught. N is replaced by 2L into N, or N into 2L. I is the current, into here R is the radius in this case, whereas here A is the radius. A square divided by 2 into radius means A square plus x is the axial displacement, in this case axial distance, whereas in this case R is the axial distance. So we can replace with R whole to the power of 3 by 2. As the axial distance is very much greater than the radius of the solenoid, we can write this as B axial is equal to mu naught into N into 2L into I into A square divided by 2 into, as A is very much less than R, we can ignore A. So we get R square whole to the power of 3 by 2. That is equal to mu naught into N into 2L into I into A square divided by 2 into R cube. Here 2 gets cancelled. Therefore B axial is equal to this expression. So B axial now again can written as mu naught into here N into 2L. N into 2L is equal to capital N. Here in the expression of M we get M is equal to N into I into, here A is not the area, here A is the radius. By multiplying this with pi, we get pi A square, and dividing with pi, we get N into I into capital A by pi. So we get in the expression 2 pi into R cube. By multiplying numerator and denominator with 2, we get mu naught into 2m divided by 4 pi R cube is the expression for the magnetic field at the axial line of the solenoid, which is similar to the magnetic field produced by the bar magnet, which is equal to mu naught into 2 into capital M divided by 4 pi R cube. So the bar magnet and solenoid are similar to each other, that is a solenoid can behave as a bar magnet. This same derivation we can also derive from the method of integration. We know that here we have taken only dx. The width of the solenoid is dx and its distance from the point P is r minus x, because from the center the dx width solenoid is at a distance small x. So for dx width the solenoid, the point P locates at a distance of r minus x. So we can write for dx width, the magnetic field can be expressed as mu naught into n into dx into I into a square divided by 2 into r minus x whole square plus a square whole to the power of 3 by 2. Here r minus x is the distance, this is the dx width solenoid, actual length of the solenoid is 2L. From this dx the origin is at a distance x. From the origin the point P is at a distance r. So from dx the point P is at a distance of r minus x. So we have replaced here r minus x, and a is the radius. A is the radius of the solenoid coil. Now by integrating this magnetic field from minus L to plus L, 0 to this end the length is minus L, and 0 to right side the length is plus L. We integrating the dx, the magnetic field produced by the width dx within the limits minus L to plus L. Then we get mu naught n into I into a square divided by 2 into r minus x whole square plus a square whole to the power of 3 by 2 integral of dx from minus L to L. Then we get mu naught n into I into a square. This integral value we get integration of 1 dx is x. By substituting the limits plus L to minus L, we get L minus of minus L, which is equal to 2L. The integration value is 2L divided by 2 into r minus x whole square plus a square whole to the power of 3 by 2. Now here by multiplying numerator and denominator with 2 pi, we get mu naught n into I into pi a square into 2 into 2L divided by 4 pi into r minus x whole square plus a to the power of 2 whole to the power of 3 by 2. when R is very much greater than A, that is the point P on the axial line is at a greater distance compared to the radius of the coil, then we can ignore the value of A from this expression. And by approximating R minus A whole square as R square, R minus X whole square as R square, that is, here X is the distance of the dx width of the coil. Then we can write the above expression as mu naught here n into I into pi r square into L into 2L. Here n into 2L is capital N into I into pi a square. Pi a square is capital A, the area of the coil, which is equal to capital M, the magnetic moment. So we can write the above expression as 2 into capital M divided by 4 pi. Here X is very much less than R, so we can write R minus X whole square as R square, where R is very much greater than A, so we can ignore the term A square. So we get R square whole to the power of 3 by 2, which is equal to mu naught into 2m divided by 4 pi r cube. This is the expression for the magnetic field at the axial line of solenoid. This expression is similar to the bar magnet at the axial line, which is equal to mu naught into 2m divided by 4 pi r cube. So the solenoid can behave as a bar magnet, so we can use this solenoid to produce the magnetic field in electrical circuits.